can hear and see me well, or well enough. Okay, so before starting, there are a few things I like to say. So first, general stuff. Aside from the lectures, we have, of course, the exercises. So I was wondering if any of you had any comments to how that worked. What's your opinion on how that worked with Färdig when you did exercises the way we intend to do it for this half of the course as well? Did it work all right, or should we change something? So no one is saying anything?
I think that it wasn't very good that only part of the students were encouraged to do certain exercises.
You thought it would have been better if everyone were encouraged to do everything?
Yes, because then, well, if I do all the exercises, it's more likely that I understand more parts of the course.
I don't know if that is maybe a sort of misunderstanding. Certainly my intention, and I would believe that that is Färdig's intention as well, is that everyone should do all the exercises, but you should be prepared to present some of them. That means you should have a strategy for how to present them. So certainly I want to stress that the exercises that we do in this part of the course are quite important. So for example, there are exercises counting the degrees of freedoms for the various groups, the UN, SUN, etc. That is clearly at the core of what we are doing, and nothing that should be skipped. You should really understand that. It's put in an exercise because it fits quite well into an exercise. It's not that hard. You can easily or fairly easily do it, but I really encourage everyone to do the exercises.
I also think that it would be nice to have a session where we can ask questions before the exercise class, like we had in the theoretical particle physics course.
Yes, I'm aware of that. That was actually Matthias Frö that did that on his spare time. So you should really thank him. He received no money for doing that. And well, we cannot count on people working without being paid. So unfortunately, it's not going to happen on this course. So that was quite unique. But I agree that it was probably good, but it's not going to happen on this course.
And I also think that it's more important to ask questions and to see the exercises get solved by someone else.
Yes, well, you can always ask me, for example, in connection with the lecture. So I try to always stay on a bit in the break and also afterwards. So I'm not going to spend hours on it, obviously, but I can answer some questions, in particular if it's not clear how to do the exercise. Any other comments? But so actually what I was after was more technical. Was it understandable? Did it work okay to present it? Yeah, okay. A few people are nodding. Thanks. Did those of you who are going to do exercises this time actually start with exercises? So no one is confirming that. So I would suggest, I know you have, of course, now the exam for Färdig's part, so this is perhaps a bit special this time. But I would suggest that you take a look at them a long time in advance and see if everything is clear. If it's not clear, you can ask me. And with respect to that, I should say as well that for the first exercise sheet, it's often a bit of a problem to find good exercises on the material that has already been covered, because strictly speaking, publishing the sheet on Friday, that should only be last Thursday's lectures. And that's a fairly small fraction of the course. Actually, there are good exercises on the material covered in the first lecture. So exercise 1 to 7 should be entirely covered in the first lecture. Exercise 8 will is in principle covered. You could well do it after the last lecture, but the particular version of the Lie-algebra that is used there we will cover yesterday, but it's a very simple exercise. And exercise 9 is hard though. It requires that you're a bit innovative. And it will only be covered towards the end of today's lecture or on Thursday, and this is why I haven't assigned any group to solve it. It would be quite good if someone could solve it, but if no one solves it, I guess I will present it myself. Okay. Also, I want to say that as I warned, I will keep updating the lecture notes. So I strongly encourage you to use the latest version. If you downloaded it before 9 o'clock or so this morning, you will have an older version and it won't follow as well. Possibly some people are wondering why I'm not making the effort to prepare slides. The reason for that is that I actually don't think it would help you. I think it is easier for you if you have the material collected in one place, so you don't have to pass forth and back between slides and so-called lecture notes. Also, I think it works quite well to use these pages instead of actual slides. So I think it would be a cosmetic change, so I'm not doing that. Instead, I'm improving the lecture notes. I should also say that on Canvas, in the individual lecture session sections, I have added some material, some notes about what material we have gone through, and I will keep updating that as well during the course. So if you missed the lecture, you should be able to figure out at least afterwards what was covered in that part. And I also intend to write what it corresponds to in the lecture notes. Okay, any sort of general questions to this course? Or comments? Okay, if this is not the case, we move on to the subject of matter, so the group theory. So I just want to remind you that last time we spoke about Lie groups and their definitions. We spoke in particular about matrix Lie groups, and we defined the concept of a Lie-algebra as being what you get when you differentiate the group, essentially. And then we studied in particular the rotation groups SO2 and SO3. Today we will continue with SO3, and we will introduce Casimir operators and step operators, which you should actually recognize from quantum mechanics. And that will bring us to some 2L, where L is a non-integer, 2L plus one-dimensional representations of the SO3 group. And now this here sounds a lot like quantum mechanics, and so it's probably something you recognize from SU2. And indeed, we will see that much of what we have done for the SO3 group up here can be carried over to the SU2 group. If there is time, we will also make more explicit the relation between SU2 and SO3. So we will definitely find that the algebra is very similar or the same. But if we have time, we will also actually make a homomorphism between the two groups. And this is what you need for exercise 9 on the present problem sheet. Okay, so let's actually get started. So maybe I should remind you that last time we just about had time to introduce this commutator between the generators of SO3. So the commutator between the generators is epsilon IJK AM in general, and then we can make matrix representations of this. Okay, and now we will use this, and we will derive a form for the exponentiation of the generators. So we will derive a form of the group elements. We will use then, this is a so-called axis angle parametrization. So what we will do is that we will define some arbitrary vector n pointing in some arbitrary direction. And then we will, with the algebra elements A, take the scalar product n dot A, being n1 A1, n2 A2, plus n3 A3. And this is then an element in the algebra, so this is what we want to exponentiate to find a parametrization. So to do so, it may seem a bit hopeless to exponentiate a matrix, but we will actually find a pattern that helps greatly. Namely, if we take this n dot A to the power third, we get some constant times n dot A. So the point is n dot A here and n dot A here. And this means that it's possible to write the Taylor expansion of this e to the power n dot A in a closed form. Okay, so let's now study this n dot A. So I remind you that this A here, we can view as a matrix, and this is just some scalar numbers standing in front of the different matrices A1, A2, and A3. So we will have then n1 A1, sorry, ni A I, a sum, implicit sum over 1 to 3 here, the same here, but now we use a different dummy index j, and the same here with yet another dummy index k. Now here, clearly ni, nj, and nk, they are just numbers, so we can pull them out in the font. And we keep the matrix structure here, and we take the element A, B only of the matrix structure. Now, this here is a matrix product. So we can write this matrix product component AB as first A, I, C, second A, C, D, third A, D, B, where of course implicitly we sum over the repeated indices C and D. Okay, and then to see what this is, I guess I must remind you that the generator AI was actually minus epsilon I A C. So the component AC of the generator A1 was then epsilon IAC. So this you can check up in the lecture from last time. And then we do the same trick with the other A's. So we have here epsilon J, C, D, and A K, DB goes to epsilon K, DB. In total, we had one minus sign there, one there, and one there. So this is our overall minus sign. Then we use a relation that we derived for epsilons. So when the epsilons share an index, as they do here, the first two epsilons, they share the index C. So this means that C is dummy summation index. Then we had a relation saying that we had one term where we identified the first index of the C. And now the first index of the C in this case of the first epsilon, this is then the next index if we are reading cyclically. So that's the I, and here we have after C we have the D standing, so it's I delta ID, and then we have the other indices, so delta AJ. And then we have minus the term where these two have swapped. So I is now connected with J and A with D here. So this is a result that we derived last time. So that's what happened to the first two epsilons. They moved over here. The third epsilon is just standing here. And so do the constants in front. Then I note that n squared, okay. So we must then use these delta functions. So for example, in the first term, we have delta I and D. So this then becomes n D. Delta A and J. So this then becomes an A. And then we have nk still standing there. And we have this epsilon still standing there, epsilon k dB. Minus minus, that is plus. And for the second term, we have that I and J are similar. So we have then the same dummy summation index here and here. So ni, ni, but ni, ni, that is nothing but n squared. And remains thus the nk and the epsilon k d replaced by a and then b. Now, the first term here is 0. Can anyone tell me why it's 0? If I say symmetry, so the reason is that this epsilon, if you recall, it is totally antisymmetric. So if I swap k and d, so k is 1 and d is 2, same as k is 2 and d is 1, then I get minus the same thing. But if I look here, those two are mapped to exactly the same thing. So I say I get epsilon 1, 2, and then I get n1, n2. But the other term where I swap them, I have a minus sign and I have no minus sign from here. So in shorter form, this is antisymmetric and this is symmetric in the same indices. So it has to disappear. So this whole thing goes to 0. That's this 0 here. And for the second element, what has happened is this epsilon has been written as a k a b with an additional minus sign just because of the identification between a and epsilon, the matrix A, or elements in the matrix A with epsilon. So this guy goes, and we are left with just minus n squared and then n dot a, so the sum over k here, and then component a, b. So this is then what we have remaining. Now, the point here is that this means that we will get an iterative pattern when we exponentiate this guy. So now we are back to this, and if we multiply it on with yet 2 more powers of n dot a, we will get another modulo 3 power and so on. So we can use this to simplify the expression e to n dot a. So let's now have a look at e to n dot a. So e to n dot a, this is, so we expand the exponent. So this is then 1, and then its linear term is n dot a. The quadratic term is 1 over 2 factorial n dot a squared, and then we have a cubic term 1 over p factorial n dot a cubed. And this is the guy we have spent some time simplifying. And then we have etc. 1 over 4 factorial n dot a to the power 4. Okay, and then what's happening here on the second line is that this guy is replaced with the expression that we just had. So this guy goes to this guy, and this guy goes to minus n squared n dot a squared. So now we take this and we collect terms. First we collect terms that, well, okay, first we collect the one, it just stands there, nothing happens to it. And then we collect terms that are proportional to n dot a. Now the terms that are proportional to n dot a, we find them here. So that is this guy. And then we have the next guy here. So this goes there, etc. So the n dot a is pulled out, and we have only the minus n square mapped to the minus n square there. And then, of course, we will have further n dot a terms, etc. And then we do the same thing for the quadratic terms. So here we collect terms that have n dot a squared. So we have then this guy going to the first term here, and then this guy 1/4 factorial going over here, etc. Then the next two lines look almost exactly the same, but what has happened is that n as a vector has been replaced by its absolute value times a unit vector. So the vector m is absolute value n times vector n hat pointing in n direction. This means that we have to compensate for the lost power of the n absolute value here. So here it's n absolute value multiplying n hat. Here it's only n hat. So this means that where we had this 1, we now have a factor n, etc. So we gain 1 power of n for all the terms in this first expression here. For the second term here, we have 2 powers of n. So here we gain 2 powers of n. So it's n squared instead of the 1, etc. And in this form, it looks much more recognizable. So now maybe, hopefully, someone knows what it looks like. Maybe, I guess this is exactly the sort of situation where someone in a classroom would say it, but here everyone's silent. Okay, so I say it myself. Also, you have it in the notes, so maybe it feels like cheating. Okay, so if we look at this first term here, this looks exactly like a sine. This guy here looks exactly like the sine, and this guy here that has been green all the time, it's now red. It goes like, it's almost a cosine. There is only a 1 missing, and it's off by a sinus 1. If it was the expansion of a cosine, we would have a 1 standing in front here. So 1 minus n squared over 2 factorial, etc. Okay, so the bottom line then is that we have managed to derive this closed form for E2, this matrix. So we have managed to exponentiate this matrix analytically. And the tricks that are used here are fairly standard and useful, so it's a good idea to remember them. Okay, one thing to note is that this e to n dot a actually leaves the vector n invariant. So if we now take n as a vector and we act e to n dot a on this n, this is then, so we use the result from up here, so it's 1 plus, sorry, we're just exponentiating the matrix, so it's 1 plus n dot a, etc. And what remains then is only n. So let's have a look at how this comes about. So we then have for the second term here n dot a acting on n. So it's this guy, and we study the component I of this guy. So we have n dot a component, and now we write this as I j and j. This does not look entirely right, actually. So I guess it should be I here. No, sorry, it is of course right. Yeah, that's right. Sorry. Okay, so this is then this start we write as n k a k, and then we take component I j of this, and then we have n j. So this is then n k can be pulled out, a matrix in matrix K component I j as here and j. And this is then, and now we use the form of a k I j. So this was epsilon k I j and j. And now again, by the same trick as before, we see that this is 0. Because epsilon is antisymmetric and nk and j is symmetric if you extend the indices k and j. So equivalently, n dot a on n is 0. So therefore, all the higher terms up here will give 0. So we are left with exponent acting on n is n. This should not be a surprising result if you think about it, because I'm pretty sure you have seen it in special cases. Let's say now that n is taken to be in the z direction, and let's say that we're rotating around the z direction. Then, of course, nothing is happening to the z-axis as we rotate around the z-axis. So this result is actually only the rotated version of that statement, so it's not so exciting. But it's important to note then that n is invariant. That is, the rotation axis is invariant. Are there any questions to that? Okay. Then let's have a look at the explicit form of n dot a. So a has non-zero entries in the components not involving the a in question. So a1 has nothing in the 1 something entries, so here or here, but has something here or here. And otherwise it's antisymmetric. So it's minus n1 there, it is n1 there, etc. So this is a linear combination of antisymmetric matrices, and that's important to note. We will see something similar in general for rotations in higher dimensions as well. Another thing to note here is that it is traceless in a very obvious way. that is, of course, something that follows for the antisymmetry here. If this matrix is antisymmetric, we cannot have anything on the diagonal, but it's a more general result than that. It will reappear later on, that is. Okay, so last time we had something called the Euler angle parametrization. Here we have finally a final form of this axis angle parametrization. So now we will take this explicit matrix form and we will insert it into this general equation that we derived up here. So that is what is happening here. So we can write down now in a closed form a rotation around an arbitrary axis as e to some length phi. So phi is the absolute value of this n from before. And then n hat, so the normalized version of n dot a. And what we have here is just the result we had above. And then one can stare at this a bit, and it's not so interesting, so I'm not going to go through it. But if you spend some time staring at this, you should be able to see that you get this matrix here. And the nice thing about this parametrization of SO2 is that it makes use of the infinitesimal generators of SO3. So before we move on, I'd like to see if there are any questions to that. Then now is a good time. If there are no questions, I like to move on, or possibly you can phrase it as move back to the Lie-algebra. So now I will consider the Lie-algebra the way physicists do it. So the way we did it before, which is simpler, is the mathematician's way of doing it. We physicists, for some reason, we multiply L with, we multiply our generator A with I, and we call it some other letter, let's say Li. And then instead, when we exponentiate, we compensate for this little I here by inserting a factor minus I. So minus I times I, that is 1. So we end up with the same expressions as the mathematician. So why do we do it this way? What's the point of this, of carrying around a few extra factors of I? Isn't it just a mess? Well, I think it is a little bit of a mess, but there is, of course, a very good reason for doing that, namely that we want to have Hermitian generators. But why do we want to have Hermitian generators? Well, the nice thing about Hermitian generators is that they have real eigenvalues. And real eigenvalues is something we like in physics because it corresponds to real observables. So for this reason, physicists pretty much always insert i's in the algebras, and we use instead Hermitian generators. So for this particular case, we take our a's and we multiply them with an I, and we get these guys here. So it's just what was before ones sitting in different places are now i's sitting in different places. And an arbitrary rotation can be written in the same form as we had it before. We just have to carry around extra minus i's, compensating for the i's that are hiding in these new generators Li. So these Li's are what physicists would call generators. And the Lie-algebra, although it is in principle spanned by the AI as before, so or minus the Li's, if you want, minus I the Li's, or the minus sign we can of course forget, but I times Li. So this is actually the Lie-algebra. However, physicists would mostly, almost always, unless they are rather mathematical, talk about these guys as being the Lie-algebra. Also, we would then like to rewrite the commutator relation in terms of the L's. So since on this side we gain two i's, one for this L, one for this L, and on this side we only gain one I, one for this L, we must compensate with an extra factor of I here. In fact, when physicists say the Lie-algebra, it's fairly common that they actually mean this relation. So the algebraic relation relating the generators rather than the linearized space around the group elements. And this here, I think you recognize quite well from quantum mechanics. So you can see that we are approaching quantum mechanics here. I'm pretty sure you had something called either L or J and some sort of commutator relation of this form where you had Lx, Ly, and Lz. And this will bring us on to ladder and Casimir operators, so it will be even more reminiscent of quantum mechanics. But let's see if there are any questions before going on to that. Okay, if there are no questions, I will move on to the concept of ladder operators and Casimir operators. So these objects are what they were in quantum mechanics, essentially. So we have studied the Lie-algebra, but it is actually quite useful to extend this Lie-algebra, or to rather extend the space that we are studying to include complex linear combinations of the generators and to consider higher powers of the generators. Complex linear combinations, such as this guy here, L1 plus I, L2, is actually not an element in the algebra. So this I would spoil the hermiticity. So if L2 is Hermitian, this guy is not Hermitian. So technically speaking, it is not in the algebra, but people are sometimes lucky and think about these operators as also being in the algebra, or if they are more careful, in the complexified algebra, where we would allow complex coefficients in front of the generators. There, of course, this would clearly be an element. We will consider this because it will be ladder operators, as you know from quantum mechanics. So we will consider L plus, that is L1 plus I, L2, and L minus, that is L1 minus I, L2. Here we also note that if we take the dagger of these operators, then L plus goes to L minus and L minus goes to L plus. These operators satisfy some useful relations. So L3 commuted with L plus minus is plus minus L plus minus, and L plus and L minus commuted is just L3. And that is something that I think you recognize from quantum mechanics and that we will use. This relation here is entirely straightforward to prove by just explicitly inserting L plus or L minus and then expanding out. So for example, we will have one term that is of the form L3 commuted with L1, and this should then give us some I epsilon 3, 1, 2, L2. So this will give us some L2, the I was there, and then I had an epsilon 3, 1, 2, and that is 1. So it is entirely straightforward to show that you get this relation, and similarly it is entirely straightforward, and I would guess that you have done this in quantum mechanics to show this relation. Can someone nod if you recognize this? Great. And these operators, ladder operators, we will use to study representations of the group. We will also use something called a Casimir operator. And we will use what's known as Schur's first lemma. This I think you should know from the first part of the course. Great. So it states that if a matrix commutes with all representations of the group element P of an irreducible representation, then it must be proportional to the unit matrix. And we will here try to construct this matrix. I think this may sound a bit funny. What's the point of trying to construct the unit matrix? I mean, you can just write it down. So of course, the statement is not trivial, so we will try to do something real. We will try to write down a general, that is representation independent form of an invariant operator. So we want a form that is valid in terms of the representation of elements in the algebra that is valid for any representation. And note that to commute with all group elements, the matrix needs to commute with all the generators, such that it commutes with E2 linear combination of generators. So if we are searching some matrix X that satisfies this, then this matrix must commute with all Li's. And the statement here is that a possible solution, a possible matrix X that commutes with L1, L2, L3 is L square. So L square is L1 square plus L2 square plus L3 square. And it satisfies this commutator. So it is invariant under group rotations. This you should also recognize from quantum mechanics, but it is an easy exercise to prove, and it is one of the exercises to prove for Friday. And this operator L square is called the Casimir operator of SO3, or for people that know more group theory, the second order Casimir operator. The second order Casimir operator, you would say, because if you have larger groups, you sometimes have higher order Casimirs, and they can be independent or independent as well. But for SO3, there is only one Casimir operator. For SU3, there are more Casimirs, 2 Casimirs. I think we can actually take the break here according to plan. But for doing that, let's see if there are any questions for a general audience. So if there are no questions or comments for general audience, I will sit here for a few minutes and see if someone asks me a question in a smaller context. And if it's a very good question that's relevant for everyone, I will repeat it in the bigger group later on. So otherwise, you can take a break. So I will sit here for a few more minutes, and if silence, I will go and then come back 5 minutes before time. It is pretty silent, but I'll stay here for a minute anyway. Okay, so it's time to return. Any questions or comments to the material so far? It would be nice to see some more people actually. I think it adds to the feeling of having a lecture for everyone, also for you to see each other actually. So you recognize each other. Okay, any questions or comments to the material so far? No. Looking how far I come, I must conclude that I have been quite slow, but what did you think about the speed? No comments.
It's fine if you go faster for me.
Yeah, maybe I was too slow then.
I personally think it was pretty good because I want to take notes while I'm listening to a lecture, and for that it was a very good pace, at least for me.
Yeah. It easily happens with slides, and I think this is quite equivalent in that sense that it goes faster. So I try to avoid that, but I'm thinking that maybe I was a bit too slow this time. Okay, so we were talking about this so-called Casimir operator, the sum of the squares. Now this is actually not an element in the algebra, so it should be proportional to the identity matrix, and that is certainly not in the algebra here. It's not traceless and it's not antisymmetric. But the nice thing is that this operator commutes with all of the iterators, so the eigenvalues of L square will stay invariant on the group transformations. So if you have a state with a certain eigenvalue and you do a group transformation on it, the eigenvalue will still be the same. So states with different values of L square must therefore belong to different representations. And we can use the eigenvalue of L square to characterize the representation. We can also express L square in terms of the ladder operators. So the ladder operators that we had up here, we now want to express L square in terms of them. So first we note that L square was Lp squared plus L1 squared plus L2 squared. I leave Lp squared. L1 squared I write as L plus L minus. In this way I cancel out the IY terms. And I get 2L1 here in the bracket, and this is cancelled by this factor 1, 4. And similar by taking L plus minus L minus, the only thing that remains is the minus plus I L2 ones from there and ones from there, and squaring this I get the minus sign from I square, which is compensated for here. So this factor in total gives me then my L2 squared. Okay, now another way of looking at this expression is to note that the L plus squared from here will cancel against L plus squared from here, and similarly L minus squared terms will cancel between there and there. So if I add these two pieces together, the only thing that will remain is the cross terms, and they are coming from here and from here. So I get 1/2 L plus L minus plus L minus L plus. We call it the order here matters. Then I can rewrite L plus L minus and L minus L plus in terms of the commutator. So I get then L3 square. I have another L3 and I keep one of them, L minus L plus, or I can keep the other one and I get this expression instead. So the point is that I have, by straightforward algebra, two different expressions for L squared involving just one generator, L3, and the step operators. And this we will use to find the eigenstates of SO2, and then we will repeat the procedure for SU2, and later on we will have a look at SU3. So now to what will be the 2L plus 1 dimensional irreducible representation VL. As we have seen, different representations can be parameterized by the different eigenvalues of L2. So L2 must then be adjusted to the representation in question. So we have VL of L squared. So this is the representation of this operator on an L dimensional space. And we can characterize the representations by the eigenvalue of L2, or this operator in matrix form, but we also want to characterize the states within a representation. The problem is that L1 and L2 and L3 don't commute, so one cannot just pick all of these to label as states. So we can pick only one actually. And if we would pick, try to, aside from the one that we pick, L3, pick another one, L1 or L2, we would find out that it doesn't work because they do not commute with L3. So we pick only one L3 to label the states within a certain representation. So the representations will be labeled in a sense by L squared, and the states within the representation will be labeled by the eigenvalue of L3. This you should recognize from quantum mechanics. So we want to characterize the states by the eigenvalues of L squared and L3, or to be more picky, their respective representations. For convenience, we may choose a nice basis, and we do choose a nice basis in this vector space VL. We choose a basis in which this guy is diagonal. And we label the states in VL according to the eigenvalues of this guy. So here I have written VL of L3. So this is the representation of L3 acting on a state LM. So L has to do with this L. So it says what representation we are talking about, and M is the state within the representation. VL L3 on the state is M and then the state. So it is an eigenvalue, or an eigenvector with eigenvalue M of this operator. And it also should of course have eigenvalues to L squared, and here we call the eigenvalue lambda. Then to find out what lambda and M can be, we will use L plus and minus defined as before. We will also use this relation, L3 commuted with L plus and L minus, plus minus, L plus and minus. And actually, I could here go on and write the L of this guy everywhere. But that will be rather clumsy, so I'm ditching this notation temporarily. So I'm talking about a particular representation down here, but I will nevertheless write just L. So the DL, that is implicit. Okay, so now we'll consider L3 on the state L plus L minus which have acted on LM. So L3 on L plus L minus on the state LM. So then what I do is that I rewrite this guy as itself. This is the first term of this commutator L3, L plus L minus, this guy, minus the other term in this commutator, that is L plus L minus L3. but that comes with a minus sign from this commutator. So this cancels this guy. So this thing is only this thing. Then we use that L3 commuted with L plus L minus is plus minus L plus L minus. And we also use that L3 acting on this M state is per definition M. So this guy just gives us the M. So it's L plus L minus M plus minus L plus L minus L M. So I collect numbers, M there and 1 there, multiplying L plus L minus. So the point then is that what I get when L3 acts on L plus L minus LM is a number times L plus L minus LM. Or in other words, this state is an eigenstate of this operator with this eigenvalue. No surprise, I'm sure most of you should recognize this from quantum mechanics. So we have found that the eigenvalues of L3 are increased or decreased by 1 unit when we act with L plus L minus. And for this reason, L plus minus is called the raising or lowering operator. So we note that the different eigenvalues of L3 are separated by units of 1. Combining this with the fact that the representation L is finite dimensional after all its own matrix representation, we note that M can only take on a finite number of values. So there is some M max. And since L plus on the state would increase the eigenvalue, L plus on this state must vanish. So L plus on L M max must be 0. Okay, so now we will use this to define properties of the maximal M. So we act with L square on L M max. Here I use a form for L square from above. It's L cubed L3 squared plus L3 plus L minus L plus on L M max. L plus on this maximal state must go to 0, so this whole term we can ignore, and the other terms will just give M or M square, because we are talking about an eigenvalue M max if you want. So we have that L square on L M max is M max plus 1 L M max. So, in other words, lambda on this state is, L square on this state, that is, well, giving the eigenvalue lambda is this thing. So lambda is this thing here. That was for the M max state, but recall that rotations do not change the eigenvalue of this operator because this commutes with all operations within the group. So this eigenvalue lambda M max times M max plus 1, that is not only true for M max, this is true for all M. So we have, in other words, found a relation between L square and M max. Now we want to figure out more. And to keep the notation somewhat uncluttered, we define L as being M max. And then we have the lambda, so this guy is L times L plus 1. So lambda is this guy. And lambda should be the eigenvalue of the operator L square. So I act with L square on my state Lm. Now I assume that I use a nice basis, so this will just give me a number. Then the Lm will hit the Lm, and it's normalized to 1. So this is just, this will then just give me the eigenvalue of L squared. But now it will rewrite L squared. First is L1 squared plus L2 squared plus L3 squared. Then I know that my L3 squared will give me an M squared. L1 squared plus L2 squared will give me something larger than 0. So I conclude that this thing here is larger than or equal to m squared lm lm. Lm lm, since the basis is orthonormal, is just 1, so this is m squared. So I conclude that L times L plus 1 is larger than or equal to m squared. Now this puts constraints on how large my m squared can be in terms of L. So taking m equal to L clearly works. So I cannot take m equal to L plus 1. But I can take it equal to L minus 1, L minus 2, etc. All the way down to minus L. Minus L squared, of course, gives me the same as L squared here. So this means that I get these options for the eigenvalues of m. So m can take 2L plus 1 different values. So the space is 2L plus 1 dimensional, and now we can connect on to the title why it's called 2L plus 1 dimensional representations. So we take then these L's to characterize the different irreducible representations of the group SO3. And to each possible values corresponds, to each possible value of L, there is a non-equivalent unitary irreducible representation. And the basis for that representation is in question is then, can then be labeled by L. I have L everywhere here as the first argument. And then I go from minus L plus 1, etc., all the way up to L. We've also said that we want states to be eigenvalues, so eigenstates of L3. So we represent then L3 by some 2L plus 1 times 2L plus 1 dimensional matrix. So we take it to have this form. If you stare at it for a while, you will see that it is traceless and Hermitian. So Hermitian is pretty obvious because it's Wheelian. And there's nothing on the off diagonals here. It's traceless because if you add up these numbers, you get 0. Okay, so we have found a representation of L3 on this space. And then we know that acting L3 on L plus L minus Lm should be m plus minus 1 L plus minus Lm. So in other words, this state is also an eigenstate of that operator. What we did not figure out is actually the normalization, because it could be a constant times the normalized eigenvector. And in fact, it is a constant times the normalized eigenvector. So L plus L minus on the state is a constant times the guy with m changed by 1 unit for some proportionality constant. So now we'll figure out what this constant is. So to do that, we write the constant squared. So we take L plus L minus on this guy. So here we have it, absolute value squared. Then we rewrite L plus when it's acting backwards as L plus dagger, similarly for L minus. And then we recall that L plus dagger was L minus. So we have the relation like this between the daggered and undaggered version of L plus minus. And then we use an equation from before, for example, that L squared is L cubed squared plus, sorry, is L3 squared plus L3 plus L minus L plus. So we use this and insert it here. And then we recall that L square on the state was L times L plus 1, and L3 gives us just M, and L3 squared gives us M squared. So we have this thing here. So the point of this is to see that when we act with L plus and minus, we do get an eigenstate, but we don't get we get the normalized eigenstate times a constant, times the root of this constant here. Now, of course, we have an absolute value here, so one could imagine inserting some phase, any phase here. That would just make things messier. So we take the phase to be unity, and we take this coefficient to be this value. This we can always do the definition of our basis vectors. So this is then the root of this thing. And this you should you probably recognize from quantum mechanics as sketch coordinates. Any questions to this? Okay. Okay, and then the eigenstates of this vector, and here I've explicitly written out that it's the L equal to 1 representation of this vector. We want them to be this guy with eigenvalue 1, this guy with eigenvalue 0, and this guy with eigenvalue -1. So this means that our L3 must be represented in this way here. So -1 when acting on the third guy, 0 when acting on the middle guy, and 1 when acting on the first guy here. So this is then the representation that we want of L3. So far it was just abstract properties without a matrix form. Now I say that I want my eigenvectors to be in this form here, and then the form of L3 follows. Before I had freedom of choice with respect to my basis. Okay, then we can study L plus and L minus on these states to figure out the matrix forms of L plus and L minus. So what has happened here is that this form here of the eigenvalue C has been used when acting the one-dimensional L plus on the state 1 minus 1. So in other words, it's been inserted L goes to 1 here, so it's 1 times 1 plus 1, and it's been inserted M, this M, so -1 here. So minus 1 times M, that was -1, and then it was L plus, so it's plus here times 1. Now 1 times -1 plus 1, this is 0, so this whole thing goes away, and the only thing that survived was this guy. So this was 1 times 2, so that gave rise to the square root of 2 there. And in the same way, the other factors here can be calculated. And we can in particular note that when we act with L plus, we get something for the -1 and 0 state. We get 0 on the 1 state. Similarly, when we act with L minus, we get something on the 0 and 1 state, but we get 0 when we act on the -1 state, as expected. This means that L plus must have the form here given by this stuff here, and L minus must have this form given by this stuff here. Now, if we take a look at this, we see that we have, for L plus, we have something 1 unit above the diagonal, as expected, because it's supposed to increase L. For L minus, we have something 1 unit below the diagonal, as expected, because it's supposed to decrease N. So we have the expected form. Now, then, having obtained the form of L plus L minus using the Clebsch-Gorlin coefficients from up here, we can also obtain expressions for L1 and L2. So L1, if you recall, was this guy. So L plus was L1 plus I L2. And L minus was L1 minus I L2. And from that we can, of course, solve for L1 and L2. So for L1, we get half this guy plus this guy, so the imaginary IL2 pieces cancel, so we get this guy here. And similarly, we get for L2 this form here. And in this space, a general, this representation, a general group element is written in this form, where the generators have this form here, L1 and L2 from here and L3 from above. An important thing to notice is that these L1, L2, and L3 are not the Lx, Ly, and the Lz from above. They are different, although the dimension of the space is the same. This is not so strange because one can always rotate the bases in the space. And this space is constructed such that we have eigenstates of L3. I'm not going to spend a lot of time on the exponentiation of these matrices. One can use the general active angle parametrization from before and find expressions by inserting the matrices. One can then use so we have this means that we can find explicit representations for rotation around the x, rotation around the y, and rotation around the z axis. But I will not spend more time on them, they are not so interesting. Let's see if there are questions to this. If there are no questions to this, we will move on to the next chapter, which is about the special unitary group. And Hugo has written this intriguing remark here, and I think that you can probably guess many of you what this refers to. If not, we will get there. But I think it looks pretty dark with respect to coming to that and today, but tomorrow, next time, on the first day, we will see what is meant with this statement. So here we will consider one of the most important groups in physics, SU2. Possibly one could even say that it's the most important group. So we will, of course, have a repetition of the definition, and we will look at the Lie-algebra, and quite importantly, we will see the relation to rotations in 3 dimensions. We will study the reducible representations as we did for SO3, and it will be easy because we will be able to carry over a lot of stuff from the SO3 case. Okay, so now the SU2 group. So I want to remind you that we're considering the special unitary group of can be described by 2 by 2 matrices with the property that d dagger is equal to 1, so d dagger is the inverse, and the determinant should also be equal to 1. And it is not hard to prove then that the general form of the unitary matrix in 2 dimensions is this guy. If you just multiply this guy with its dagger, and if you require that a squared plus b squared is equal to 1, you will see that you get u dagger u or u dagger is equal to 1. So it satisfies the constraint of being u as in unitary. It does actually not satisfy the constraint of having determinant 1. So we will make some more restrictions to it to obey that. Now, parametrizations of unitary matrices are actually often done in terms of the sigma matrices. That's very handy. So we will here introduce the Cayley-Klein parameters xi 0, 1, 2, and 3. So we will rewrite this matrix in terms of these parameters. So let's actually do that explicitly. So I want to take my u and I want to write it using these parameters. So down here I have a, so it's simple. It's xi 0 plus I xi 3. Up here I should have a star. So it's xi 0 minus I xi 3. Down here I should have b, so it's xi 2 minus I xi 1. And up here I should have minus b star. So now correct me if I get the minus signs wrong here. So minus xi 2 done. And for the xi 1, I have a minus from here, a minus from there, and a star. So this should give me minus xi 1. Don't be if I'm wrong here, could be. Okay, so we can then write this unitary matrix of this form, and we will now see that this can also be written as a linear combination of sigma matrices / Pauli matrices. So we will then write this. The statement is that we can also write a unitary matrix of this form. So xi 0 times the identity matrix. We can easily see that that is right. We have xi 0 here. Minus I xi dot sigma. So we should then have minus I xi 3 up here, right? Because sigma 3 is 1 minus 1. We should have the same thing with a relative minus sign down there, and we do that for sigma 1, which is 1, 1. We should then have minus I xi 1 there, so I missed the I there. And for same thing off the diagonal. And finally, we have that sigma 2 is minus I. So we have a minus sign from there, a minus sign from there, and we have a minus I from there and a minus I from there. So it should be a minus xi 2 up here, and indeed this is what I wrote here. And then we should have a relative minus sign for the guy in this component, and there is a relative minus sign for that guy. So that expression is hopefully correct. Let's see if I can move it. Maybe I want to use it down here. Okay, so this was u in terms of the Pauli matrices. Now we want this u to have the determinant 1. So we want determinant u to be 1. Now, if we take the determinant of this guy, so we take this element times this element minus this element times this element. So here from the diagonal, we see that we get psi 0 squared, great, as we should have. And then we get minus I times plus I, that is 1, psi 3 squared, as we should have, great. And then we calculate the off-diagonal components in the same way, and we should find minus psi 1 squared and minus psi 2 squared. So for the special unitary group, we have another constraint, namely this constraint here. The determinant should be 1, so psi 0 squared plus psi 1 squared plus psi 2 squared plus psi 3 squared should be 1. Only have three parameters to describe 2 times 2 unimodular matrix. Now, actually, in general, in an exercise, we will prove that SUN can be parameterized by n squared minus 1 parameters. So this means that having found 3 parameters, we know that we have found a complete parameterization. And this is the important result that I was saying before was hiding in an exercise. So you should understand that before the end of the course. Okay, so now if we take 3 parameters, and 1, and 2, and then 3, and we're combining into some vector n, we may choose the Cayley-Klein parameters as psi 0 is cos of some angle, and psi vector is n hat, so the unit direction times sine of this angle. So n hat is the normalized vector, and the length of the vector is hiding in the parameter phi here, which is root n1 squared plus n2 squared plus n3 squared, so the length. With this, one can write down again an explicit parametrization for this u in this form here. This is actually again coming from the general axis angle parametrization. It should not be SO2 here, it should of course be SO3. Also, one can say that that was an SO3 result, and so why can we use it for this SU2? That's then a good comment, but the answer will become obvious. I think many of you know it. Okay, so we will use the Pauli matrices quite a lot. So before moving on, we should explore some properties that they satisfy. So we have sigma I sigma j is 1 times delta I j plus I epsilon I j k sigma k. Now let's check that for a few cases. So if we have, for example, sigma 3, this is 1 minus 1 times 1 minus 1. So this is 1, 1. And the epsilon guy is 0, and so it is only this delta guy that remains. So we are happy, and it would be very surprising if we found something else for 2 and 1. You can do it if you want to get this result. Then let's also check this for some other matrices, like sigma 1 and sigma 2. So now this delta guy should give us 0. So sigma 1 and sigma 2 is then 1, 1 is sigma 2, sigma, sorry, 1, 1 is sigma 1, sigma 2 is minus I. So let's see what we get. We have this guy hitting this guy, so this is I, 0, 0, minus I. So this is I times sigma 3, and it shouldn't be I epsilon I j k sigma k. So let's see what epsilon I would have. I would have epsilon 1, 2, 3, and this is 1. So I have indeed recovered this. Good. Okay. So now having written down the product of sigma matrices like this, sigma I, sigma j, is in general 1 delta id plus I epsilon id k sigma k. We have for the commutator sigma I commuted with sigma j, that this is 2I epsilon id k sigma k. This we can just see by copying this result from up here. So for equal indices, we have this guy minus itself gives us 0. For unequal indices, we get 2 contributions from this epsilon. In the same way, one can write down the anti-commutator of sigma I and sigma j and obtain 2 delta I j times 1. So these two can be obtained from that relation. And now let's then have a look at the SU2 algebra. In the remaining 3 minutes. So we want to write SU2 of the form E to some matrix. Using this, we can actually find a constraint on the generators x here. So I take here my SU2 matrix dagger times my SU2 matrix. Now, since this is a unitary group, this thing should be 1. So if I expand it, I should get 1. So expanding the first one, I have 1 plus alpha xi dagger. And the second guy, I have 1 plus alpha xi. And then I have higher order terms. But the point is that to order 1, it should be 1. So this implies that this guy must be cancelled by this guy. So this guy plus that guy, that is this thing, must be 0. So this gives us a constraint on the generators. Here, there's no I here, so we're back to the mathematician's convention. So you can see, and you should see in one of the exercises, well, it's actually not needed. You can pick mathematicians or physicist conventions as you want, but if you insert the I here, you should get that it's Hermitian instead. Now you get that it's anti-Hermitian. Okay, so with this constraint, we see that the generators of SU2, so the SU2 algebra is given by complex 2 by 2 matrices in the defining representation with the property that x dagger x is equal to 0. Also, we should have that the trace of x is 0. So we can take these matrices to be essentially I times the sigma matrices. And that will then span the SU2 algebra. And now we will get back to the physicist's choice of Hermitian matrices. And then we could, in principle, take the generators to just be sigma 1, sigma 2, and sigma 3, but we will actually normalize them with factor 1/2, as is frequently done. And the reason for that is that with this normalization, we get this commutator here. So do you recognize this guy? Yeah, I'm sure many of you do. So if I had written L here, this is exactly the commutator that we had for SO3 using the Hermitian generators. So we have seen then that we have actually the same algebra for SU2 and SO3. So their algebras are isomorphic. And then later on, we will see if the groups are also isomorphic or not, or will happen. But that will be on the first day. So let's first see if there are questions to this material. So I will also stay around here until most of you have left the room to see if someone wants to ask me a question in a smaller context, and otherwise you can also ask questions by email.
So I was wondering if how this is related to quaternions. So SU2, are they related to union quaternions?
They are related to quaternions. So if you multiply the quaternions, you should essentially, so the quaternions are essentially 1, sigma 1, sigma 2, and sigma 3. They should square to -1, so they cannot be exactly that, but they must then be I sigma 1, sigma 2, sigma 3. So they can be represented by I sigma 1, sigma 2, sigma 3. So they are 1 to 1 with the quaternions. If you take the 3 sigma matrices and you take the diagonal 2 by 2 matrix as well. But it's nothing we will talk about really in the course.
Okay, thanks for the information. I think it's interesting to connect it to.
Yes, quaternions can be used in physics, but they are not so often used in physics. So this is why we're not spending a lot of time on it. But you gave me a good idea. Maybe I will make an exercise on it actually. Yeah, maybe I will make an exercise to find a connection to the quaternions because it should be easy.
Yeah, thank for the help.
Any other questions? So, any comments, perhaps? So, I take this as a replacement for standing around in the lecture hall. So I intend to be as approachable as in front of the whiteboard. So feel free to ask questions. And I'm also very interested in receiving comments.
I think that type of lecturing was really helpful.
Sorry?
I think that type of lecturing is particularly helpful to me, at least. It's going through the lecture notes very slowly.
Yes, so I think that making slides would not help because one would only have the material in 2 places and one would have to switch forth and back, and it would just be more confusing. But one could, of course, consider having sort of tablet lectures or having whiteboard lectures, although it's remotely. I think people may have different opinions about what's best there.
Yeah, maybe for some more tedious expressions, it probably could be helpful to switch to a whiteboard, but so far it has been quite okay, I think.
Good to hear. Did you possibly have a look at the exercises?
I personally haven't looked at them yet. No.
Okay, so Lucas, Adis, do you have any comments or questions?
No, I was waiting to hear the other questions because it's always interesting.
Yeah.
Well, goodbye.
Yeah, I guess there are no more questions, so I guess we finish the session then. So thanks for today and see you on Thursday.
All right.